these weeks. Today we will continue with our couple of talks related to mixtures and how to analyze environmental exposures in a more holistic way. We are very lucky we have with us two excellent researchers, Dr. Chris Gennings and Anna Young. If you want to share your slides in the meantime. A brief introduction. Dr. Chris Gennings is a professor and director of the Biostatistics Division in the Department of Environmental Medicine and Climate Science in the Icahn School of Medicine of Mount Sinai. And her main research interest is on the design and analysis and the design and development of methods for studying complex mixtures. For example, she recently developed and led the extension of a mixture method called weighted quantile sum regression, as well as development of different personalized nutrition indices. And she will be the first speaker, but we also have with us Dr. Anna Young. Anna Young is Associate Research Scientist in the Department of Environmental Health and at Emory Rollins School of Public Health. And she's specialized in environmental epidemiology as well, with a strong background in data science. And her research focuses mainly in reproductive and carcinogenic impacts of human exposures. And today, they are going to talk to us about the development of mixture methods for high-dimensional omics data to investigate environmental risk factors of disease, also with a very nice case study at the end of the session. So please bear and keep with us. Well, whenever you want, Chris, thank you very much, and the floor is yours.
Thank you very much for the introduction and for inviting us to do this. I'm delighted to be here. It's one of my favorite topics, as you guys might be aware. Let's see if I can get the page to turn. Okay, there we go. Sorry, got a little technical problems there. So one question, to start thinking about mixtures, it all depends on what your research question is. It's not one size fits all. The research question that we're focused on is there a mixture effect? So let me start by saying, what do I mean by what is a mixture effect? So the mixture effect is this concept of something from nothing that's been in the toxicology literature now for some time. And it's the idea that individual components that may be at very low levels, one at a time, but the joint action of them together can have significant effects. So if we ignore the fact that these chemicals often have such a relationship, then we can be underestimating risk. And of course, that's the concern if we're talking about mixtures. So what we're interested in is if we're looking at a set of C exposures, we're interested in trying to identify if there's a subset that do combine jointly to increase that risk of whatever adverse effect or whatever our hypothesis is that we're interested in. And we're going to do that by creating a weighted index. And by focusing the inference in terms of a single degree of freedom test, then we have a more powerful test. And then at the end, what we're going to do with this weighted index, we'll have empirically estimated weights. And from that, then we can characterize the components that seem to be contributing to this mixture effect. So the thing about the WQS regression then is what we do is we put all the chemicals or all the components, they don't have to be chemicals, but whatever the components are that make sense to be in a index. We have to put them on the same scales, and by doing that, then that means that we can interpret the weights that we estimate per component. And so we put them on the scales of quantiles. And an advantage of quantiles is then we don't have to worry so much about extreme values. Often exposures have very skewed distributions, and we don't want to have influential observations and things. So we could do deciles or quartiles or whatever you choose there. And an advantage of using a weighted index is that we don't have to be so worried about multicollinearity or the reversal paradox because of the complex correlation pattern that's typical among components that we look at. And we do that by using something called an ensemble step. And I'll describe that in two different ways. Anna, at the end of this talk and her presentation, will be using one of those, but my examples will be the other form of the ensemble step. Okay, so what is weighted quantile sum regression? So here's a little cartoon about that. Suppose we have four, these are phthalate metabolites, but suppose we have four components and they have some complex correlation pattern. So this is meant to be a correlation of those with some that could be positive, some that could be negative, whatever, some that might be higher than others. So what we do is per subject, we take the concentration of each of those components and put them into these quantiles like I talk about. So we can think about that as ranking them. So if we're talking about deciles, then we would score something, say, from 0 to 9 for the deciles. So we take our study subjects and we split them into parts. And the parts then will be the training part and the validation or a testing set. So the training part, typically we use 40%, and I can explain that in a little bit. So we take the training data, or the subjects, the training subjects, and through a nonlinear, and that's going to be nonlinear estimation because we've got weights that we have to estimate in a sum of the weighted index multiplied times the regression coefficient, the beta, and we get weights. Here they sum to 100%. But then by resampling, by going in and randomly selecting with replacement from that same 40%, another set of to train on, we might get slightly different weights. And this is, again, taking into account this correlation among the components. So suppose we do that 100 times, and then we can take average weights or average those weights across those 100 here bootstrap samples. And then with those final average weights, then we can take the holdout data set and create a WQS index using the weights we just estimated, but the quantiles and the exposures from the holdout data set. And at the end of the day, what we would anticipate is that the association in the training set is going to be a little bit attenuated in the validation set because the validation set didn't have, wasn't trained. That's not the training part. But we get the betas or p-values or whatever from that analysis. But what we're going to do, so this is what that looks like a little bit more, with equations. So you can see we're going to split the training in the 40% and the validation 60%. But this is what I mean by the nonlinear regression model. So we have the beta times the weights that we're estimating in the first step. And an important part of this that you'll have to think about when you do an analysis is in the nonlinear step, we can actually constrain the beta to be in the direction of our hypothesis. So if we're looking at an adverse effect, then we could say, suppose positive beta is an adverse effect that we would anticipate in our study, then we can constrain the beta in this step to go in that direction. And this gets to the point of a lot of times when we're doing such a study, we have selected chemicals to study because we think they're adverse. We don't think they're beneficial. And so it makes sense then that it's possible to constrain them. So we do this bootstrap step. We get the average weight across the, say, 100 different bootstraps in that ensemble step. And then that gives us a WQS that then we can estimate in just a generalized linear model at the end of the day with the holdout data set. So like I said, we've got two different strategies for the ensemble step. The first part is what I just described, where we randomly select the observations with replacement and get the distribution of the weights across those random sets, and then we can take the average from that. But the other part is instead of randomly selecting observations, we can randomly select components. So here we would have the full set of, say, N observations, but we could randomly select a subset of the full components and do that many times and then average across that. And this is the approach that Anne is using in her metabolomics analysis. So if C, the number of components, is bigger than N, and often it could be much bigger than N, then we can use this random subset component. So this was part of dissertation work from Gala Bello, and then Paul Curtin did a simulation study of this that's been published. The other thing that's sort of an extension from the original WQS paper is this idea of repeated holdout data sets. So this is Eva Tanner, who sort of championed this idea. What I just described is where we take our subjects and we split them into the blue people, the training people, and the pink people, the test people, right? And we get the estimated weights here, and then estimate the beta on the holdout set. But what Eva worked on is said, well, what if we do that splitting multiple times? So we're splitting the validation from the testing group. And so here you see we can get different distributions of the pink and the blue there. But by doing that, suppose we do that 100 times, for each analysis, we would get an average set of weights from that splitting. But if we do that splitting many times, then we would get a distribution of weights across these different repeated holdouts, as well as distribution of the betas. So that's what I'm going to show you in what's coming. So somehow it didn't go. Okay, here we go. So an analysis strategy. One thing that you can do, of course, usually we'll have covariates that we want to adjust by, but you might want to start just by trying to estimate the WQS, the weighted index, without the covariates, and maybe we start without a constraint, just to kind of see what's in the data. Then we might put in our covariates to see if there's a difference between when we do the analysis with the covariates. But oftentimes, like I said before, we might want to constrain in the direction of the hypothesis. If we're saying these are chemicals that have been selected for study because we think they could be adverse, and we're trying to get a weighted index from that, a mixture effect from that, then we know the direction that we're looking in. If we don't have such an hypothesis, which might be the case in metabolomic data, where we might want to look in different directions, then we might want to determine, well, is there a dominant direction? So we really have only 4 scenarios. One is there, a positive association, meaning beta 1 is greater than 0? Is there a negative association? Beta 1 is less than 0. We could have associations in different directions that could be different weights in different directions. And our colleague Stefano Renzetti has just published a paper that we call the double index WQS regression. So you might want to look at that. But that's beyond what I'm going to talk about today. And of course, the 4th scenario is that there is no association. Okay, so the other thing that we've done recently that I think is really cool is the idea of a stratified interaction model. And I'm going to demonstrate that now with these data. So this is published by Eva Tanner again, using the Selma cohort, which is a pregnancy cohort out of Sweden. And here you see we've got a whole bunch of chemicals that were measured in early pregnancy, about 10-week median of 10-week gestation. And then we're looking at adverse effects. And here today, I'm going to talk about 7-year IQ of the children. But the interesting thing here is, notice in this column, this is the percent above the limit of detection for these chemicals. So we've got phenols, plasticizers, other short-lived, the PFASs, and then persistent chlorinated chemicals. But interesting, and I'm not going to spend a lot of time on that, but the green marks here are the components that said, if you're doing a risk assessment of single chemical analyses, one at a time, these geometric means would be well below the point of departure, or the biomonitoring equivalent level from risk assessment issues, indicating that this should be okay. There's only a couple of PFASs here that would be against that. But what we're going to see is that because of the mixture effect, we do see evidence of an association. And that's of course of concern in terms of risk assessment strategies. Okay, so I'm going to kind of show you the stratified interaction WQS regression sort of by an example. But this is the idea where you can put in the WQS estimates, but you allow them, say, if you have a categorical variable like sex, then you can allow the weights to be different for the different sexes, and also the weights can be different. And so that's what we see here. So we've got boys and girls. These are estimated simultaneously. We're not splitting the data to do the stratification. We're estimating them all together in this sort of idea of an interaction model. But what you see is if you can see the little dots there, those are the particular estimated weights, say for bisphenol F, in one realization of the 100 bootstraps, right? Sorry, of the 100 repeated holdouts. And then you see the box plots in there as well, right? And this is then the average of the weights that you see in the boys and the girls in this divergent plot to kind of give us sense of there could be differences in the weight distribution, that's the average distribution. For example, DPHP may be more important in the girls, whereas bisphenol F and TCP may be more important in the boys. This then is the confidence interval on the beta coefficients from these different 100 repeated holdouts. And the blues, the boys, where we see it's significant. The 0 is not included in that confidence interval. The red is for the girls. And of course, 0 is included there. This is just a little bit of a plug, but I have developed something called the My Nutrition Index, which is a personalized metric of nutrition based here on food frequency questionnaire mid-pregnancy. And the interesting thing here is it ends up being positively associated with 7-year IQ, whereas in these EDCs, in the boys, we have a negative association, meaning lower IQ at 7 years. So this is the kind of resulting table that we get in such an analysis, where we get here the average estimate across 100 repeated holdouts and the standard error, and then the percentiles for a confidence interval. But here, of course, the MNI was positively related to the 7-year IQ and is significant. But the reference group here are the boys. And what we see is for the boys, the beta 1 is negative and significant. Here's the interaction that we get in this kind of analysis. What we're saying is then this is like a beta 1, 2. This is like the interaction. It's testing. Is there a difference between the boys and the girls? And here, the confidence interval on the interaction is not significant, but we can take it a step further and say, well, what is the slope? We get right here the slope for the boys, but what is the slope for the girls? The slope for the girls is going to be the difference between the two plus the slope in the boys, right? So the beta 1 plus the beta 1, 2 would be like a beta 2, or the slope for the girls. And so we would add maybe the mean or the median here, minus 2.13 plus 1.98. And you see we've attenuated the effect. The girls don't have as strong of an effect. And in fact, the girls are not even significant. And that's what we saw in that figure. But this is just to kind of show you in this kind of analysis what you can get from having an interaction term. So the other thing is, at the end of the day, now here in this analysis, we've shown that there seems to be an association for boys. So let's sort of interpret what that means. And we're using something called the Busgang criteria. And this is Stephanie Busgang, who kind of championed this strategy. So the idea is that if we're doing 100 repeated holdouts and we have, say, 90% or more above, the threshold here is the equi-weighted part. So this is saying if we had 26 chemicals, then 1/26 would be sort of the threshold, where we say if the typical exposure or the typical weight is above that threshold, then we say there seems to be an association. If it's below it, then we don't have evidence of that. But here in the Busgang criteria, we say, well, if more than 90% of the weights are above that threshold, then we would say that component is a probable association to the outcome. So here we'd have bisphenol F and TCP. But there are other chemicals that we might have more than half of them above that threshold, and we'd say that those may be possible associations. So we're kind of giving a little bit of a less of an association, less strong statement about those that are possibly associated. And you see there's a bunch of them here where the diamond is above, which is the mean, or the little bar, which is a little harder to see, but in the box plot is above the threshold part. Of course, the other interesting thing about this is we do have chemicals here that are well below, it looks like for PCBs, all of them are below that threshold. So we would say that's possibly not associated. Probably not, I said that backwards, probably not associated with the outcome. And that's kind of an interesting thing to talk about as well. Okay, so then just to wrap up, here's sort of the R code. That we have a GWQS package in R. So this is sort of a general way of coding that. whatever outcome we have here. Here, I'm assuming that it's a continuous variable, so I'm using a Gaussian family distribution. So WQS can't be in your data set. We're going to estimate that WQS with the weights. Here, I've done a stratified interaction. So we've got female is a 0-1 variable for female, for male or female, and then we've got the stratified part here, which has to be a factor here. The variable sex has to be a factor. And so then we have, covariates we can add there. We have a named vector in R that is the name of the chemicals that are in the, that we want to have in our analysis. We've got the data set. The Q is the quantile. So here the deciles. We have 60% that we're holding, at the cut. We're leaving 60% out for the validation set. In this case, so this would be like what Anna's going to use in her analysis. Suppose we have the case where the number of components, say, is really large. Here, I assume, say, 1,200. We might use the square root of that as the number of variables we want to randomly select with replacement. So, and that would be the random subset version. And then we would do that 2,000 times and then average across those. Here's the part about the constraint, which you have to kind of think about. This is saying, do we anticipate in the positive direction or the negative direction? And here we would anticipate maybe in the negative direction, so it's not positive, so it's false here. We do want to constrain, so we're going to say that. And because we have the interaction term, we would have a variable. This would be what the other group would be. So here would be the males. The females. Do we anticipate that it would be negative as well? Of course, if you have 3 groups in your strata, then you could have 2 different levels here for the additional groups. We have a seed that we can put so we can reproduce the analysis. And then this plan strategy makes it a little bit more efficient in running. And this is where we say we have 100 repeated holdouts. So you can change that based on what you want to use. Okay, so in this analysis with the little illustration, we did identify a mixture effect of jointly acting EDCs that seemed to decrease the 7-year IQ. We were adjusting by covariates. There was a significant association in boys, but not in girls. But in this case, there wasn't a significant difference in the slopes, but still we had different sort of inference between boys and girls. And we used the Busgain criteria to identify probable and possible components that might be associated with the decrease in IQ. And we also saw the My Nutrition Index was significantly associated with an increase in 7-9. So prenatal exposure. So that's what you might anticipate. Better nutrition in pregnancy might improve outcomes for the child. And so this is a metric that might seem to work with picking that up. Okay, so next, Dr. Anna Young is going to describe her work. She's got some really cool data. She's going to be using the random subset WQS, and her C, the number of analytes, greatly exceeds the sample size. And some work that she's really clever in the way she's dealing with this, but it's difficult when C is so big, how to manage and display and then characterize the results with large C. So there are still, places for extensions in what we've done with WQS. So let me just sort of identify again. We've got a team here that's done all of this work. This is Stefano Renzetti, who's did the double index WQS, and he also manages the GWQS R package. He's a really friendly guy and good, very helpful. So that's all for me, and I appreciate your attention. I'm going to hand it off to Anna.
All right, thank you, Chris. That was such a fabulous overview of this method you've developed. And I'm really lucky that I've had Chris as a close mentor in applying her methods to this untargeted chemical exposome data, and especially the random subsets implementation that you heard about is a really unique and powerful new way to apply this to high dimensional untargeted data. So let's see. All right, yeah, so I'm going to talk about a case study that Chris Gennings, my advisor, Doug Walker, and I have been working closely together on applying this to the cancer exposome. So just as a brief background on the type of data we're looking at. So current high-resolution mass spectrometry approaches can now detect over 100,000 known and unknown environmental chemicals and endogenous metabolites in human blood. And this is really helping us go from not just testing hypotheses about a small number of known exposures, but adding on to this hypothesis discovery and being able to generate new hypotheses about potentially unknown risk factors. And I want to highlight that even though we can't confidently identify every chemical in this data, we can still statistically analyze the health effects of even the unknowns here. And just a brief note on the distinction between the exposome and metabolome. So in a single analytical run, we can get measures of both in human samples, but the internal chemical exposome is mainly referring to the environmentally derived chemicals of exogenous origin, as well as their biotransformation products in the body. Then the metabolome focuses conceptually on the endogenous metabolites that are of internal origin in the body. So we recently did a scoping review looking at studies reporting to evaluate the exposome in terms of cancer. And we only identified 14 eligible studies. Only one of these leveraged untargeted chemical exposome profiling techniques, and that was specifically for breast cancer. We know there are over 100 types of cancer. So this is a really largely unmet application of the untargeted exposome in the field of cancer research. So I'd like to talk about the work that my advisor has been leading for his R01, along with Chris as a co-I, which is building the Cancer Exposome Atlas. So we're not just looking at exposome in one population at a time, but looking across many different cohorts. And we've been working over the past few years to collect over 4,000 different cases of blood cancers. And these are all from cohorts that were prospective, and so they had blood samples collected many years before diagnosis. So that enables us to better look at potentially causal risk factors. And so we have data so far from the CLUE cohort, and so that's what I'll present on today. So the CLUE study enrolled 25,000 adults, followed them for several decades, and we nested a case control cohort within it that had 222 cases of non-Hodgkin's lymphoma, NHL, as well as their individually matched controls. What was great about this study is that they had baseline blood samples collected in 1974, which was an average of 21 years before diagnosis. And then for a smaller subset of those participants, they had a second blood sample collected in 1989, which was an average of 9 years before diagnosis. And we really wanted to see what chemical exposures might be driving future NHL risk, as well as which metabolic pathways might underlie those associations. And just to demonstrate the complexity of this data, so these samples were analyzed in Doug Walker's laboratory by Catherine Mullins, and with liquid chromatography, high-res mass spectrometry, we detected nearly 100,000 chemical features. And we're running these samples through gas chromatography as well, but that data is not ready yet. But you can see across these two instrument columns, the HILIC and C18, there are many features. 85,000 were detected, and at least a quarter of participants. Many of them we could tentatively annotate as possible chemical matches based on external databases. And then several hundred we could confidently confirm the identities of using in-house standards. So if we were to use a traditional approach, running univariate regression for each chemical feature one at a time, we may look at Manhattan plots like this and see that in these single chemical logistic regression models, there are about 6,500 features associated with NHL risk at a loose significance threshold of 0.1, or maybe around 3,000 features at p less than 0.05. But we know this is a massive multiple testing concern and could detect false positives by chance. So it becomes really important to correct for multiple testing, which in this case, we would find that there are no chemical features significantly associated with NHL risk. So there are these challenges with statistical power here. And not only is power a concern with these univariate analyses, but as Chris mentioned, we can have concerns about multicollinearity. And if we just look at one chemical in a model at a time, there might be co-confounding if different chemicals have a shared source or a shared exposure route or shared biotransformation pathway. So that's really where these mixture methods are coming in. And so for applying this to weighted quantile sum regression, we did want to narrow down the mixture we put into the model first. So for example, we restricted to chemicals that were detected in at least a quarter of participants. We did also filter to chemicals that had a potential association with NHL risk using that loose threshold of P less than 0.1. This is because we wanted it to be a biologically relevant mixture and sort of represent the cumulative effects of what might be related. And then finally, one of our concerns was about endogenous metabolites influencing the mixture index. So we restricted to chemicals that had potential identities based on external databases as exogenous environmental chemicals. Now, of course, that does come with a trade-off because you either are more certain that you're excluding these endogenous metabolites or even biomarkers of disease. But at the same time, you may not be capturing as many unknown chemicals. So there are probably different approaches to this, but this is what we're doing in this study. And we did 2 separate models, one for each instrument column, which led to mixtures of size 1839 and 940. As you remember, our sample size is 444. So we definitely have more chemical features than we do sample size. And that's where the random subsets implementation comes in that Chris talked about, which is just an amazing advancement that was made by her and her collaborators. And so instead of randomly subsetting observations every time, we're randomly subsetting smaller sets of chemicals every time and helping to decorrelate that data, avoid co-confounding, and also support this untargeted high-dimensional scale of data. So we used 2,000 random subsets here, and then we use 100 of the repeated holdouts, as Chris mentioned, to improve generalizability. Some other parameter choices we made, because this was a nested case control study, so we had cancer cases matched to their own controls. And we thought this was really important for anyone using a study design like this, because the repeated holdouts will randomly partition individuals into that training set and test set. But in our case, we wanted to manually partition our participants based on pairs, not individuals. So in this way, each case control pair was either in the training set or the test set together. And it was really a great function in WQS is that you can actually give it the manual rows with the repeated holdouts. We also didn't use the automatic quantization that WQS can do in that single function. And this is all in collaboration with Chris, so I really appreciate her help with this. So we decided to use deciles, but having one of those deciles as a separate 0 quantile that was just representing non-detects or zeros. And then the other 9 deciles were quantized just on the non-zero data. And I'll explain a bit more about that when we get into sensitivity analyses. And then finally, we adjusted for our matching variables as well. So I want to highlight first, before I get into our results, that this is preliminary unpublished data, so it could be subject to change. So what we found with the cumulative mixture effect is that each decile increase in the mixture index was associated with a 53 times higher odds of being diagnosed with NHL in the future. That was averaged across repeated holdouts and assuming the effects are in the positive direction. The odds ratios were similar for both data from the different instrument columns. And you can see on this box plot, when we look at the index of each participant, that the cancer cases do have a much higher score compared to the controls. So this is a very high odds ratio. And I want to remind everyone that, we were looking at mixtures that had at least 900 chemicals that were already nominally associated with NHL. So we're seeing this cumulative effect of many chemicals simultaneously. But Chris and I have been working in the past few weeks on other ways to interpret this data, especially because if you see, even just in this box plot, that a lot of the index scores for each participant do fall on these kind of middle deciles because we're aggregating across many chemicals. It's unlikely someone would have, be in the first quantile for most of the chemicals. So we looked at a per standard deviation increase in the index as opposed to just a decile increase. And those odds ratios are about 4.6 and 4.7. So to do that, we had to look within each repeated holdout and then take the averages. And now we were also able to see which important chemicals may be driving those overall mixture effects. So Chris mentioned the equiweight threshold and how a chemical may be important if its average weight is above that threshold that represents the hypothetical of every chemical contributing exactly equally. So there were about 1,200 chemicals in total across the two instrument modes that met that criteria. But to go into the boosting criteria that Chris mentioned, we can look at the weights within repeated holdouts. And what we found here is that 951 chemical features were possible contributors, meaning that they had weights above the threshold within at least 50% of holdouts. And then for even stronger chemicals that were probable contributors, there were 59 that had weights above the threshold within at least 90% of holdouts. And this graph shows just a small subset of 36 features here. And the way we were looking at it, which is based on the boosting papers as well, is the distribution of weights through these box plots. And you can see how they compare to the equiweight threshold. And then the bar charts representing the percent of holdouts that had the weight above the threshold. What was great here is that among all of these chemicals, there are over 40 annotated as possible novel PFAS, plus many flame retardants, plastic-related chemical annotations, and pesticide-related chemical annotations. And most previous research on environmental risk factors of NHL focused on pesticides and legacy PCBs. So this really showed that there could be an array of different types of chemical classes that are contributing to risk. And just to highlight the comparison between cumulative risk and individual risk. So I just told you that the odds ratio we found was about 4.6 per standard deviation increase in the mixture index. If we took all of the possible or probable chemical drivers of the mixture index and put them on their own into separate single chemical regression models. So this is not done within WQS, just literally taking the results and running 1,000 different regression models. The odds ratios we would find would be about 1.2 to 1.8 per standard deviation increase in those individual chemicals. So you can see how risk might compound, and we get a better picture of total risk while also dealing with potential collinearity and co-confounding between chemicals. So I'd like to briefly touch on some sensitivity analyses that we've been running over the past couple months. So for example, we relaxed the significance threshold for inclusion of chemicals in the mixture from the get-go. So we had done P less than 0.1. We've now tried P less than 0.2 and P less than 0.3. What we seem to be finding is that it does increase the mixture effect and number of important features a little bit, but at some point it doesn't contribute much. It plateaus and eventually seems to actually go down if you include too many irrelevant chemicals. And we think that's because if you're including, say 10,000 chemicals, then the random subsets each time may be picking a random small set of chemicals that aren't contributors. And so there's more flat effects coming out. We've also tried using a stricter detection threshold, like chemicals over 50% of samples. As you expect, it reduces the odds ratio and the number of important chemicals. At some point, increasing random subsets didn't seem to help in our case. The difference between 2,000 and 4,000 barely saw any difference. What was really interesting is that, so we did repeated holdouts based on the matched pairs from the beginning. And then I ran an analysis to see what it would look like if we just did the default partitioning by individuals. And the mixture effect was about a third of the size. So it went down a lot. And I didn't expect this change, but what we've been hypothesizing is that the holdouts could be creating unrepresentative data sets. For example, if the controls happen to be of higher ages based on the randomization, and we don't have that matching that controls for similar distributions between cases and controls, that it may not be as valid there. And then something else that was really interesting was changing from the manual quantization of exposures. If you remember, we wanted the non-detects to be their own separate zero quantile to just automatic 10 deciles. And what we found is that the mixture effect with the default was extremely inflated and in a non-interpretable way. And we think that's because, chemical features could have the first 6 quantiles are all 0, and then the next 4 could have really big jumps in the positive levels. So those were some things we've learned. This is still very much in the works, and we're still trying to figure out what all of this means. And I'll let Chris jump into at the end if she wants to add anything. So finally, I want to talk about how we could use WQS in metabolomics as well. So if you remember in this study, we had a baseline blood sample, we had another intermediate blood sample. These are both pre-diagnosis, and then future cancer diagnosis. So what we could think about is, what if we have this chemical mixture index based on the baseline blood sample data? This is just one variable, which is really helpful, because if we want to look at the metabolomics, which is also, this high dimensional data at the intermediate time point, it's much easier to have this one variable and then this high dimensional set, and then seeing how that affects lymphoma risk. And the idea is meet in the middle analysis, where we use this R package metapone, which predicts functional metabolic pathways that are enriched for each of these associations. So we want to see which metabolic pathways were significantly enriched with exposure and then with outcome, and which ones overlap and might be underlying pathways. We used a few different approaches. We looked at the metabolites that are just the untargeted features at the second time point. We also looked at this as the change in metabolites between time 1 and time 2. And then because there's a smaller sample size for longitudinal data, we also looked at the metabolites at baseline, which is cross-sectional with the WQS chemical mixture, but does have a much higher sample size. So here's what we found. There were 16 significantly enriched pathways on the y-axis that overlapped between one of the mixture indices and the NHL cancer outcome. So you can see here, this grid is when we look at the pathways from the baseline data, pathways from the longitudinal time point 2 data, and then longitudinal pathways from the difference between T2 and T1. And all 16 of these pathways have some level of evidence of being potentially carcinogenic or anti-carcinogenic, which I think demonstrates the power of this type of method to find potentially intermediate pathways. Just as a brief highlight of some other ways we might be able to use WQS. So if we wanted to not just look at the index as one variable, but actually the chemicals WQS told us might be important contributors to the mixture, we could run a correlation network analysis where we're looking at the relationships between each of the WQS chemicals and then the enriched pathways from metabome. And these pathways here are represented by the first principal components of all the metabolites within that pathway. So there are some fun ways to use WQS, and I want to conclude this study by highlighting how it may help us close the gap on the missing heritability of disease. For cancer, the average heritability is only about 10%. The other 90% is estimated to be initiated by non-genetic environmental risk factors. There's a lot we still don't know about that. And so this type of discovery-based approach can help us see what other types of chemicals may be driving our total risk. So overall, the WQS with random subsets especially is a powerful method that actually works with untargeted chemical exposome data at that high dimensional scale. And it can help us identify cumulative mixture effects, bad actor chemicals, and potential underlying metabolic pathways. And this gives us the power to elucidate previously unknown risk factors and even disease etiologies, which may help future research with potential therapeutic targets. So with that, I'd like to thank my advisor, Douglas Walker, who's an associate professor at Emory and head of the Clues Exposome Laboratory, as well as, again, Chris Gennings, who's been a fantastic mentor over the past year and into my K99 grant. So I've been so lucky to have her advice on this, and I'd like to thank all of our other research collaborators and NIH funding. Great. So thank you everyone for listening. And Chris, if there's anything you want to add, feel to jump into.
I think you did a super job, Anna. Thank you. It's an interesting analysis.
Thank you very much, both Chris and Anna. I think you did excellent presentations, and the works that you have presented. It's really nice. Can you hear me? Sorry, I think I ran out of battery. Can you still hear me?
Yes.
Yeah. And I think that the method you present is going in the direction that many methodologies are being developed now, adopting these resampling procedures to do more robust inferences. We have some questions. Maybe I can split those for, I guess that they are for Chris or for Anna. We have first question that is about if you can talk about the differences between WQS and quantile G computation regression.
Sure. Yeah, QG comp. The difference is in QG comp, first of all, there's not an ensemble step. It really is a G computation, but the analysis, the estimation of the parameters is done in a generalized linear model that has all of the components all together. So, and then the betas are estimated in that way. And so my concern there would be that we could have multicollinearity issues and the reversal paradox where there's some positive and some negative just based on the correlation of the components. The QG comp, and then the next step in QG comp is they just take the estimated betas that are positive and add them up, and the estimated betas that are negative and add those up, and then the psi function is the sum of those. So again, it's a different strategy. It's not really an extension of WQS, although it sounds like it should be, but it's really not. It's a different way of thinking about estimation. And without the ensemble step, I am concerned about multicollinearity with QG comp.
Okay, and this in part answered another question from Yuka in Tika about if there is any concern with collinearity or cross-correlation. I guess that you mentioned that it's not a big deal, no, with your extension of WQS.
With QG comp or with
WQS?
With WQS. So yeah, I mean, so remember WQS, we are estimating things together in the nonlinear step in terms of the weights, but we're not estimating, and then we do that multiple times, and by doing it multiple times and then averaging across that's the ensemble step. Then that sort of accommodates that multicollinearity thing, right? Or that complex correlation pattern. If you just do an analysis once and you've got a set of components that might be highly correlated, you don't put weights on all of those. You put weights on maybe a subset of them or one of them, right? And then you do it again, and so the correlation pattern, you might choose another one. So I think the ensemble step allows you some robustness across that correlation pattern, and not just doing it one time.
Yeah. And well, there is one question about if the method can handle categorical exposures, like all the regression methods suffer with categorical exposures.
Right.
But I wonder if there is a way to include them as dummies, or have to test the performance according to this category.
The main thing is the components have to make sense in an index, but they have to be on the same scale. Now, like what Anna showed is we don't have to have equal number of observations in each sort of decile or each quantile, but we need it to be on the same scale so that the weights make sense in comparison to each other, right? There's some colleagues I have here that took some of the World Trade Center data that was questionnaire data about exposures and things, and the data there were I don't remember how many categories there were, but let's say 3 or 4 categories per question. You could just base instead of quantiling, you just base it on that. If you want to have a mix of continuous and categorical, I mean, I don't know where that makes sense, but if it does make sense, as long as you put them in the same number of components, I think that's fine. Because at the end of the day, you're trying to compare what's the weight of this component versus the weight of this, how they might compare that way. So the application is important there in terms of what makes sense to be in the index.
Okay, and also some questions for Anna about the possible extensions of this work in other type of omics data, like genomics or epigenomics.
Yeah, I think if there's a reasonable set of whatever biomarkers, exposures that you could see contributing to the same index towards the same sort of effect, I think you could apply in that way if you can get them on the same scale as Chris was saying. I haven't seen it done with other omics. Have you, Chris?
Yeah, I mean, people are working in that area. Yeah.
I wondered, like, about the computing times for this, because you run an analysis with a lot of features, but also you do the resampling and holdout. It was demanding in terms of time or resources.
We were finding it can get demanding, especially when you're estimating the weights, both for the random subsets and then on top of that, the repeated holdouts. So when we did 100 holdouts and 2,000 random subsets, that's 2,000 times 100 times those for those estimates. And that's why we did pre-filter some of the chemical features to get a smaller mixture to put in the model, about 1,800 features in that mixture to help with the computational time. A lot of the sensitivity analyses I've been running have been taking several weeks, so it can get intensive.
We do it on your laptop.
Yeah, everything we've been running is on the cluster, which I don't think my computer would even be possible to do.
Yeah. Okay, and I have 2 questions from my side. It's about this new extension. Is there any paper where you test its performance in terms of prediction or any other type of performance against other methods in different situations, like to detect small effect sizes or according to dimensionality of the data set? Have you proved that these extensions is actually more powerful than others?
So the extensions being the repeated holdout?
Yeah.
I have not done such a comparison. There were some people kind of doing that, addressing the issue of random seeds and how that might impact. So they were comparing different These were, I can't remember her name, apologies, up at Columbia, but she was addressing things about the impact of those random seeds. And I think she did that on the same data. Yeah, I haven't done that, but there are people that are kind of working for comparing across methods. But let me just point out, though, the different methods have different research questions, and so I don't think it's the good strategy to say, does the WQS answer the same question as BKMR, the Bayesian kernel?
Yeah.
It's a different question, right? So I think there's sometimes interesting side by side, just to say, well, do we have evidence of interaction? So that's the BKMR. Do we see evidence of nonlinearity? That's the BKMR. In a WQS with nonlinearity, we could put quadratic terms in with WQS to see, a WQS quadratic term to see if it looks a little bit nonlinear, but that's not really the point of WQS, right? So I think different methods have different questions. So I think you need to make sure you're aware of what the question is you're sort of going after with the method that you choose.
Okay. And for the threshold that you presented at the end, once you have the model to interpret those individual features that contribute to the mixture, this threshold now is computed with within the package with some function, or which is the way of identifying the threshold? Yeah, sorry.
The threshold is just 1 over the number of components. So
okay.
The number of components is equi-weighted. And in terms of showing that is reasonable strategy, I was part of an EU study called EDC Mixed Risk, where we used WQS to identify components in that Selma cohort. There we were looking at, I think it was based on 2.5 year number of words that the child was speaking, and which is a predictor of IQ later on. But we chose components that were identified with WQS, and then that mixture was constructed based on typical mixtures of the geometric mean in the Selma moms, and that mixture then was evaluated in vitro and in vivo assays, and we saw causal associations, right? In those assays, you can say that mixture showed, so it's like the mixture is fixed, and it's like 1x is the geometric mean. So we say, well, what if it's 0.1x or 10x or 100x? So you can get a point of departure from that mixture, in these different assays. So at that point, you really are showing a causal relationship that was suggested by the weighted WQS index in a pregnancy cohort in observational data. So I think that combination of observational with, experimental studies is kind of an interesting way to go. And then we took that, once we sort of found a point of departure from it, it turned out it was a xenopus, the embryos for thyroid dysregulation. Then we used that point of departure and came back in and asked questions about sufficiently similar, were the moms, and we also did it in the US population, women of reproductive age, are they sufficiently similar to that mixture that we evaluated? And if they were, then what's their exposure above that point of departure? And we could, it's kind of like a hazard quotient at that point, and you're saying how high is your exposure relative to that point of departure for the mixture that you're sufficiently similar to. And so all of that, I think is a really interesting way of sort of combining observational and experimental studies of mixtures. So there's, and that particular paper is in a Science paper. I think it came out a couple years ago, but Niccolo Caporali is the first author of that. But it was a big EU consortium called EDC Mixed Risk that did that.
Well, that's great. And I don't know if there is more questions. Well, there is one about the availability of the double index method that you presented from one of your collaborators. Is this available with this extension called resampling?
It is.
Well, with the help?
It is in the newest version of GWQS, and it's run similarly to what I have said. You're estimating simultaneously the weights for components that are in the negative direction. So you say in WQS, and then the positive direction would be PWQS. So you run it by saying Y tilde, in PWQS plus PWQS. But the component, the part that makes it complex is Now you've got the same set of components and you're trying to put weights on some to go positive and weights on the others that go negative. So you really have to sort of pull them apart. So Stefano had the idea of putting in different kind of penalty functions. So you got to figure out what that lambda penalty function should be. So there's a little bit of work that needs to be done with that. It's not, you don't just sort of pull it out of the package and run it. You got to sort of work on that. So he does in his paper that came out, I think last year, Renzetti is his last name, describes, you know, strategies of how to run that, but it is available. We need to extend it to the random subset analysis. It doesn't really work yet for that, but it does for the bootstrap.
Okay, thank you very much. And thanks again, Chris and Anna, for your presentations and participations. And thanks everyone for attending today. It was a great session. Next week, we will continue. You are more than welcome with us as well. We will talk about metagenomics. The talk will be given by Dr. Bill Pimenov, and it would be at the same time of the week. So thank you very much and see you next week.
Thank you. Thank you for the invitation.
Thank you so much.